Hello, so today I'll be presenting my final project, which is on unbiased inverse volume rendering for transient imaging. Inverse rendering is the process of reconstructing 3D scenes from 2D images, and this can be used for many different practical applications outside of computer graphics. Performing inverse rendering involves solving an optimization problem. So suppose we have a 3D scene that is parameterized by a set of unknown variables and that we have calibrated images of the scene. Then we want to optimize the values of the unknown variables such that if we render an estimate of the 3D scene, the difference between our rendered images and the actual images is minimized. To do this optimization, we can use a differentiable render, which estimates the gradients of the image with respect to the scene parameters, and then uses these gradients to update the values of the scene parameters. Differentiable renders can be specifically designed to simulate different types of imaging sensors, such as transient imaging sensors. So unlike conventional sensors, transient sensors take advantage of the fact that the speed of light is finite, and they accumulate photons into separate images based on their time of flight from the light source to the sensor. We can simulate this type of sensor using transient rendering, which will produce an image sequence instead of a single image. Transient imaging is useful when the scene contains a scattering volume, such as smoke or any other physical medium that lets light scatter within it. So since photons may scatter many times before reaching the sensor, rendering and inverse rendering for scattering volumes can be very computationally intensive. But luckily, we can use a specialized Monte Carlo sampling strategy for inverse volume rendering called differential ratio tracking. And using this sampling method results in unbiased and low variance gradient estimates. So this slide shows that for inverse volume rendering, differential ratio tracking produces better results than the normal sampling strategy, which is called delta tracking. Here, the first row shows the initialization of the scene estimate, and the goal is to reconstruct the scattering volume in the last row. Also, the 5 columns here correspond to 5 sensors that are just imaging the same volume. You can see that the differential ratio tracking method reconstructs a volume that is very close to the reference. So the existing implementation of differential ratio tracking is built on top of Mitsuba 3, which is an open source differentiable render. And for my project, I added support for transient image data to this render so that we can perform unbiased inverse volume rendering with transient image data. And this slide shows my results, where I successfully recovered the scattering properties of a volume using transient image data. So here, the leftmost column shows images that would be produced by a conventional steady-state sensor, while the other columns show individual frames from transient image sequences. The second and third rows are just intermediate results, so we can focus on the fourth row and compare these final results with the reference images. The reconstructed volume seems to match the reference pretty well in both the conventional image and the transient image sequence. And here are additional results. So I performed the optimization process using 5 sensors, but the previous slide only showed images from the first sensor. So here the 5 rows correspond to the 5 different sensors. And in conclusion, I extended a differentiable render to support transient imaging data while using a specialized sampling strategy for inverse volume rendering. And in general, extending differentiable renders to support different imaging sensors and physical scene representations will make inverse rendering more useful for various applications. Here are my references, and thank you for listening.